Hello and welcome to our final topic in this course, which is hypothesis testing. We shall treat this in two parts. This is the part one. A hypothesis is a statement about the value of a population parameter developed for the purpose of testing. It could be about the values of several population parameters. Now, the act of testing or hypothesis is a procedure based on sample evidence and probability theory used to determine whether the hypothesis is a reasonable statement and should not be rejected, or it is unreasonable and should be rejected. And this is what we will explore in this session and the next. And by the end of this session, you should be able to define a hypothesis and define a hypothesis and hypothesis testing. You should be able to describe the 5 steps involved in hypothesis testing. You should be able to distinguish between one-tailed and two-tailed tests of hypothesis, and also be able to conduct a test of hypothesis about the population mean. Okay, so this is how the presentation is structured, and our texts as usual. So let's begin with the principle of hypothesis testing. So I indicated earlier that a hypothesis is a claim or statement about the value of either a single population parameter or about the values of several population parameters. Okay, so this is a hypothesis, right? Or a statement, which we may want to test to see whether it is true or not. Women are paid less on average than men. Now, hypothesis testing is about making decisions. So, as I indicated earlier, the procedure is based on taking sample evidence and applying probability theory to determine whether the hypothesis should be accepted or not. Now, in hypothesis testing, there are 2 conflicting statements about the value of the population parameter. Now, the first is called the Null hypothesis, denoted H0, and then the second is the alternative hypothesis, denoted H1 or HA. The Null hypothesis is a statement about the value of the population parameter which we believe to be true, but the alternative is a statement that is accepted, or the claim that is accepted if sample evidence shows otherwise, okay, shows that the Null hypothesis is untrue. For example, we may want to test the mean age of level 200 students being 20 against the claim that it is not 20, okay? So in this case, the mean age of level 200 is 20 years will constitute the Null hypothesis, and then the mean age is not 20 years will constitute the alternative hypothesis. Now, to test the validity of this hypothesis, we must select a sample from the population, calculate sample statistics, and based on certain decision rules, either accept or reject the hypothesis. Okay, and I indicated to you earlier that the null is initially presumed to be true. Okay, so we can make an analogy of the court of law. Okay, where the accused person is presumed innocent, which is the null. Okay, unless the evidence proves otherwise. So we go to court. You are presumed innocent until proven guilty. Okay, so that's it. Now, in making decision, we are bound to make errors. And in hypothesis testing, there are 2 types of errors we can make. The type 1 error, where you reject the null hypothesis when it is true. In other words, you will be convicting the innocent, right? And then the type 2 error, accepting the null when it is false. That is, you let the guilty person go free. So we summarize the potential errors in hypothesis testing in this table nicely, type 1 and type 2 error. Now, what are the steps involved in hypothesis testing? Now, invariably, we have to make a decision. Where do we place the decision line? Now, the point is that we wish to avoid both type 1 and type 2 errors. So sometimes it's possible to alter the decision rule to avoid one type of error, but reducing one type of error increases the chance of committing the other type of error. Hence, there is a trade-off. Now, we are more concerned with type 1 error, and we wish to make it as small as possible. So we set type 1 error probability to a particular value. Conventionally, this is 5%. And this 5% is known as the significance level of the test. And it is denoted alpha. So alpha stands for the probability of rejecting the null when it is true. That is type 1 error, right? And we want to minimize on type 1 error. It seems to be more serious, right? Convicting the innocent, right? Now, so the significance level is complementary to the confidence level. So 5% significance level is equivalent to 95% confidence interval. Okay? Now, the decision is made on the basis of a test statistic. And a test statistic is a value determined from sample information used to determine whether or not to reject the hypothesis. Now, what we do is to compare the critical value. We compare the critical value to the value of the test statistic that we computed. And the critical value is the dividing point between the region where the null hypothesis is rejected and the region where it is not rejected. Now, let's take an example quickly. Now, how long do CFLs last? So the question here is, a manufacturer of compact fluorescent lamps claims its products last at least 5,000 hours on average. Now, a sample of 80 bulbs is tested. The average time before failure is 4,900 hours, with standard deviation of 500 hours. Now, should the manufacturers claim that its lamps last 5,000 hours be rejected? Because the sample evidence is saying that it's 4,900. Now, to test the hypothesis, we first state the hypothesis. So, denoting the mean hours by mu, the null says that the mean is equal to 5,000, but the alternative is saying that the mean is less than 5,000. Why did we state the alternative being less than 5,000? You see, we wouldn't worry if the mean actually exceeded 5,000. So we could have written the null as greater than or equal to 5,000, but it doesn't change anything. Okay? And give the fact that we've written the alternative as being less than 5,000, it means we're dealing with what we call a one-tailed test. We'll talk about this in detail shortly. The null hypothesis is always a precise statement with the equal sign in it. So it's either equal to or less than or equal to, greater than or equal to. So you would always find the equal sign in it. Now, once you state your hypothesis, you choose your significance level, right? So we're saying conventionally, let's choose 5%. So our alpha is equal to 0.05. Now, if the alpha is 0.05, it means your critical value will be 1.64, because we're saying that the critical value is that z value which is exceeded with a probability of 0.05. As simple as that. We've dealt with this earlier, so I'm using these terminologies for you to appreciate it. So that's how. So the table is here to show you how we obtain the 1.64. You could alternatively use 1.65. It doesn't change anything. So since it is saying less than, it means our rejection region is in the left tail, right? So the 5%, and we're saying that this area to the left of minus 1.64 is 0.05, okay? So the rejection region is to the left of minus 1.64. So if we calculate our test statistic and it is to the left or it is less than our minus 1.64, we have to reject the null hypothesis. So based on our sample evidence, we have the mean of 4,900. Now the question we want to ask ourselves is that, is 4,900 far enough below 5,000? In other words, is it more than 1.64 standard errors below the 5,000? Okay, so let's compute our test statistic. Now, so we need to standardize our sample mean, right, as we saw. So our z is equal to x bar minus mu divided by s over square root of n, where our s is the sample standard deviation, our n is the sample size. So given the values, we obtain our z to be minus 1.79. Now clearly, our test statistic, which is minus 1.79, lies in the rejection region because it's less than minus 1.79. So we need to reject the null hypothesis. Now the question is that 4,900 is 1.79 standard errors below 5,000. So it falls in the rejection region. Hence, we can reject the null hypothesis at the 5% level, right? Now, the point we are making here is that if the true mean were actually the 5,000 being claimed by the manufacturer, then we would have it means that if that were the case, then there's less than 3.67% chance of obtaining a sample evidence such as X bar, which is 4,900. Now let's get this straight. We are saying that we're making this decision with an error level that we're willing to accept of 5%. But given what we've obtained, it means that the error level we are potentially or actually obtaining is 3.67, which is less than what we're willing to tolerate. Okay, for this reason, we reject the null hypothesis and say that the mean life of the CFL bulbs are actually less than 5,000. So we can outline the steps. You first state the hypothesis, the null and the alternative. You choose your significance level, and then based on that, you determine your critical value and state your decision rule, compute your test statistic, and then you make a decision. Now let's talk about one-tailed versus two-tailed test. Now the earlier example looked at a one-tailed test. So the rejection region was just in one tail of the distribution, in the left tail. Now, were we to use a two-tailed test, we would have written the alternative as mu not equal to 5,000. So not equal to 5,000 means it could be less than or greater than. Okay, so that's it. But when will you use the two-tailed test? Now, if you are only concerned about falling on one side of the hypothesized value, then you would use a one-tailed test, okay? Because as I indicated earlier, you wouldn't want to reject the null if the sample mean were anywhere above 5,000, because it's actually good for customers, right? Now, one other reason you might use a one-tailed test is from theory. For example, if you're testing the the slope of the demand curve, we know it is downward sloping, it's not upward sloping, so it will be one-tailed. But if you are unsure, use a two-tailed test. And we want to emphasize this, that you never choose between one-tailed or two-tailed on the basis of sample evidence, because the fact that the sample says that it is 4,900, you say it should be one-tailed test. You don't do that. Now, let's take another example which depicts a two-tailed test. Now, it is claimed that on average, or it is claimed that an average child spends 15 hours per week watching television. A survey of 100 children finds an average of 14.5 hours per week, with standard deviation of 8 hours. Is this claim justified? We want to test a 5% level. Okay, fine. Now, we want to emphasize that the claim would be wrong if children spend either more or less than 15 hours. So the rejection region is split across the two tails of the distribution. Okay, so since we are testing at 5% and it is two-tailed, we need to split it 2.5% apiece. Now, for the 2.5 apiece, it means that the z value should be 1.96, right? So you state that now mu is equal to 15. The alternative is mu is not equal to 15. At a 5% significance level, our critical value is 1.96. So we will reject a null if the computed statistic is greater than the critical value of 1.96. Now, our test statistic is computed using the information. The mean, sample mean is 14.5. The population mean is 15. And then we divide this result by standard deviation over square root of the sample size. It gives us 0.625. Now, because 0.625 is less than 1.96, we do not reject the null hypothesis. Okay, so this is how you do it. Now, another way to determine whether or not to reject the null hypothesis is to use what we call the p-value approach. The P stands for probability, so p-value means probability value, right? Now, so let's return to our earlier example of the CFL bulbs. Now, the test statistic Z equals minus 1.79, and it cuts off 3.67% in the lower tail of the distribution. What this means is that the probability that Z is less than minus 1.79 is equal to 0.0367. So 0.0367 or 3.67% is called the p-value for this example. Now, since the p-value that we have obtained is less than 0.05, the test statistic must fall into the rejection region. Now, what does the p-value measure? It measures the probability of obtaining a sample statistic as extreme as the 4,000 that we got were the null hypothesis true. So we're saying that if the null hypothesis of 5,000 hours were actually true, okay, the probability of obtaining a sample mean of 4,900 will be 0.0367. Now, the probability value is so small that it is telling us that it is highly unlikely that the sample mean will be 4,900, where the null hypothesis is true. So for this region, we have to reject the null hypothesis. And that's exactly what we did. So if the p-value is less than the probability, is less than the significance level, we reject the null hypothesis. And we do not reject when the p-value is greater than the significance level, and in this case 0.05. So there are two ways in which we can reject. We either use this when the absolute value of the test statistic is greater than the critical value, we reject, or when the p-value is less than the significance level. This brings us to the end of part 1 of session 10. I'll see you in part 2 shortly.